All right, we're diving straight into the heart of the atom to tackle two incredible forces that could literally define the future of humanity: nuclear fission and nuclear fusion. Both of them can unleash a staggering amount of energy, but as you're about to see, they are not the same thing at all, not even close.
So yeah, that is the big question, isn't it? Fission, fusion, they both have nuclear in the name, so they must be pretty similar, right? Well, no. How they work, the kind of fuel they need, and the consequences of using them, that's where they couldn't be more different.
Here's the simplest way to think about it. Fission is all about breaking things. It takes a big, heavy, unstable atom and smashes it into smaller pieces. Fusion is the opposite. It's about building. It takes really light little atoms and squishes them together to make something bigger. One is the powerful but flawed reality we've been using for decades. The other is the clean, incredible dream we're chasing.
You know, to really get why we're so obsessed with fusion, we've got to start with the tech that kicked this whole thing off. So let's break down nuclear fission, the process that's been lighting up our cities and kind of haunting our nightmares for the better part of a century.
Okay, so the key word here is unstable. Think of a heavy atom like uranium-235 as a really wobbly, oversized tower of blocks. It's already on the verge of falling apart. All fission does is give it one tiny little nudge, in this case from a single neutron, and boom, the whole thing splits. And in that process, a ton of energy is released.
And here's the magic trick, or the scary part, depending on how you look at it. The process feeds itself. When that first atom splits, it doesn't just release energy, it also spits out more neutrons. Each of those neutrons can then go and hit another uranium atom, which splits and releases even more neutrons. 1 becomes 2, 2 becomes 4, 4 becomes 8, you get the picture. That is the chain reaction. It's the engine inside a nuclear power plant and also the terrifying force inside an atomic bomb.
And that chain reaction, well, that's where we get to the real heart of the issue with fission. It is an unbelievably dense and powerful way to make energy, but trying to control that fire, well, it comes with some very, very serious risks.
I mean, just look at this number, 439. That's how many fission reactors are humming along right now across 30 different countries. They're a huge part of our global power grid, generating massive amounts of electricity without pumping out carbon emissions, which is a huge deal.
But, and this is a big but, here's the other side of that coin. The leftover junk from splitting all those atoms, it's nasty stuff. We're talking about byproducts like cesium-137 and strontium-90 that stay dangerously radioactive for thousands of years. We still don't have a perfect solution for storing it. And then there's the ever-present fear that if you lose control of that chain reaction, it could run away from you, causing a catastrophic meltdown. This is exactly why we're so desperate to find something better.
Okay, so if fission is like carefully taming a tiny atomic bomb, then fusion is the dream of bottling up a star. It's the exact same process that powers our sun, and for decades, it's been the absolute holy grail of clean energy research.
So instead of splitting heavy atoms, fusion does the complete opposite. It takes super light ones, usually special types of hydrogen called deuterium and tritium, and smashes them together so hard they merge. They form a new helium nucleus and a spare neutron. And here's the mind-blowing part. The new helium atom actually weighs a tiny bit less than the 2 hydrogen bits that made it. So where did that mass go? It was converted directly into a huge blast of energy. That's Einstein's famous E = mc squared in action. So let's just put these two head-to-head for a second. Fission needs rare, heavy uranium. Fusion can, in theory, use hydrogen from seawater. Fusion gives you about 4 times the energy bang for your buck. Fission leaves behind that nasty radioactive waste for millennia. Fusion's main byproduct, harmless helium, like the stuff you put in party balloons. And the safety? This is the kicker. A fission reactor can melt down. A fusion reaction is so incredibly difficult to keep going that if anything goes wrong, it just, poof, it stops. A runaway reaction is physically impossible. I mean, on paper, it's not even a contest.
So you're probably thinking, okay, this sounds perfect. Why don't we have fusion power plants everywhere? Well, it turns out that building a star on Earth is, ridiculously, mind-bogglingly hard. It's one of the biggest engineering challenges we've ever attempted.
Just get a load of this number, 100 million degrees Celsius. That's what you need to get those hydrogen nuclei moving fast enough to overcome their natural instinct to repel each other and actually fuse. It's hotter than the core of the actual sun. And since no material we know of can survive that,
We have to hold that superheated gas, or plasma, in place using insanely powerful magnetic fields.
And believe it or not, that insane temperature is just the price of admission. The costs are astronomical. The engineering is on another level, and the powerful neutrons that fly out can slowly make the reactor parts themselves radioactive over time. But there's another huge problem that doesn't get talked about as much: the fuel. And this is a major roadblock. One of the key ingredients, tritium, is incredibly rare. The entire planet's supply is only about 20 kilograms. Now, a single commercial reactor would need about 300 grams a day. You do the math, it would burn through the whole world's supply in just a couple of months. The plan is to have the reactor breed its own tritium, but that's another massive challenge on top of everything else.
So with all these insane challenges, the main strategy in fusion has always been go hotter, get bigger, build stronger magnets. But what if? What if that's the wrong way to look at it? What if the answer isn't hot, but cold? This is where we get into some very unconventional and pretty controversial territory.
This story comes from McCain Lee, the guy behind a company called Quantum Kinetics. He says that after surviving a really bad car accident, he had this vision, a voice in his head that set him on a 7-year mission to achieve something the scientific community has mostly dismissed, so-called cold fusion.
So let's just break down what's being claimed here. On one side, you have mainstream hot fusion, warehouse-sized machines, 100 million degree temperatures, magnetic bottles. On the other side, Quantum Kinetics claims they can do it at low temperatures in a device the size of a paint can. They claim it's not about heat at all, but about creating this thing they call a quantum kinetic well to make atoms change. Now, this is way, way outside the scientific mainstream, but it just goes to show you what kind of out-of-the-box thinking this incredible challenge is inspiring.
So that's where we are. We've got the technology that works now, but it's risky and leaves a terrible mess. And then we've got this incredible dream for the future, but it always seems to be just over the horizon. What we choose to do next could define human civilization for centuries.
Yeah, this quote really nails it. Getting fusion to work isn't just about building a better power plant. It's about ending our reliance on fossil fuels. It's about clean, abundant energy for everyone on the planet. It's the kind of discovery that could change everything.
This really sums up the race, doesn't it? Fission is our current champion. It's working, but it's got some serious flaws. Hot fusion is the top contender, the one everyone's betting on, but it's still a long way from the finish line. And then you've got the wild cards, these alternative ideas. Total long shots for sure, but you never know.
And that's the bottom line, isn't it? We've unlocked the power of the atom, but now we face a massive choice. Are we going to stick with the embers of fission and just keep managing its dangerous legacy? Or are we finally going to succeed in taming a star and light up our future with clean, limitless energy? It's one of the biggest questions we'll ever have to answer.